All right. So welcome all of you in the today's session on the one and two dimensional NMR spectroscopy for the chemist, a problem solving approach. So this is the eighth session, and I'm Vijay Rane. I'm a Prime Minister Research Fellow in the IIT Delhi, and uh, here, as we have seen in this uh, in this course regarding the one and two dimensional NMR spectroscopy, right? So we have already covered the 1H NMR and we are moving toward the 13C NMR spectra, right? So before going to start the problems, does anyone have any problem or any topic that we need to discuss here before going to start the session? Floor is open for any question answer. If anyone have any question, please let me know. All right, if you don't have any question, I will just directly start to the problems that I have taken from the assignment. So here is the first question. In the question itself mentioned the natural abundance of the 13C isotope and the nitrogen 15 isotopes are respectively. So here are these the table which shows the isotope and the NMR active nuclei. So here mention these are the NMR active nuclei. NMR active nuclei and their spin quantum number as well as the resonance frequency in Tesla as well as the natural abundance here given. Here, for example, for 1H, the natural abundance is 99.98%. So among all the, let's take the example of this molecule. Let's take the methane. And we have the methane stored in the, let's say, some sort of container. And in this container, among the hydrogens, here in one molecule, there are four hydrogen attached. So if you have the 100 hydrogens, that is, there are some molecule number of molecules which contain 100 hydrogen. Among that, about 99.98% hydrogens are the 1H hydrogens and they are NMR active. Again, we know the hydrogen have the its isotope, right? The deuterium, that is we mention it as a twice H1. This is the deuterium. Uh, we can also refer it as a D2, right? So it has the spin quantum number about 1 and has the natural abundance about 0.0156%. So in this way, in the question it mentioned, we have to give the natural abundance of the 13C isotope, which is, you can see here in the table for the 13C, the natural abundance is about 1.1%, right? And for the 19F, the fluorine 19, which has the natural abundance about 100%, right? So you can select the correct option based on this table. So moving to the next question, the gyrometric ratio of the nitrogen 15 is nearly 10 times smaller than the 1H. As a result, option first is given, the energy separation between the 1H spin and the 1H spin state and the 15N spin states are identical. This is wrong because they are not at all identical. The next option is the 15N spin energy states has the 10 times smaller separation than the 1H energy state. The option C is the nitrogen 15 has 99 times smaller energy separation between two spin states than the 1S spin state. And the D option is the 1S spin state has 100 times smaller energy than separation in the nitrogen 15 spin states. So if you look at this one, so as it mentioned, the gyrometric ratio is nearly 10 times smaller. So as a result, what happens? The nitrogen 15 energy state has uh, here 10 times smaller separation between two energy state of the 1H. So the option B is here is the correct option here. There is no any relation in terms of this 99 times smaller energy state, or here as mentioned also the 100 times smaller energy state. So as the gravimetric ratio of this nitrogen 15 is 10 times higher, so the nitrogen 15 energy states has 10 times smaller separation than the 1H NMR energy states. So option B is the correct option here. If you look at the next question, in this next question, it is mentioned in the molecule containing three chemically inequivalent carbons, the combined 13C spectrum are. If the molecule contains three chemically inequivalent carbons, so have the carbon A, B, C, right? And carbon C. So the first option given, one of the carbon 13 states and other two do not give any signal. This is obviously wrong, because obviously it is inequivalent, right? So the other two should also give the signal. So option A is the incorrect one. The major isotoper of the carbon 12 isotope, but it doesn't have anything to do with this 13C NMR spectrum, right? So this is also the incorrect option. The third is the superimposition of the spectra of three individual isotoper of the molecule. So it means they have superimposable, I mean, they have maybe comparable intensity or anything. And the fourth option is the isotopes contain all the three carbon simultaneously in 13C excited state. Sorry, 13C state. So if you look at this option, the option A we have already neglected. Option B also we have neglected. In between options C and D, the D itself mentioned the isotope must contain all the carbons simultaneously in the 13C states. This is wrong, because not all the carbons will be in the 13C state. Option C here, the correct option. The superimposition of the spectra of three individual isotopers of the molecule. This option here is the correct option, or the most uh, accurate statement given here in this one. Another one is the fourth problem. The proton decoupled. Itself mentioned proton decoupled 13C spectra of molecule. The molecule we have given here. The number of transition that can be detected. Number of transition detected here. Transition, it means number of signal we can say, right? Signals, number of signals that detected from this molecule. So if you look at the structure of this molecule, so it has the one carbon, then another carbon, further CH2, right? So if you give the numbering to this one, 1, 2, 3, 4, and 5, there are 5 different types of carbon, right? 5 different carbons are present in this molecule. So it will give the total 5 transitions in the proton decoupled spectra, right? So here option is the 5 option is the correct option here, right? So in this one, we just need to identify what are the different types of carbons present in the molecule. So there are 5 different types of carbon present in this molecule. So it will show the 5 different transitions. So let's take the same example. Let's say the question number 5. If it is not a decoupled spectra, so what will be the splitting pattern? So if it is not a decoupled spectra, then in that case, what will be the splitting pattern for this molecule will look like? So in this one, so this is, let's take, yes, Yes, please, you can
Second
ask the
question
question.
for, I think you missed one carbon.
Uh, oh, all right. So it is one, two, three, four. All right. So option B is the correct option. Yes, here. Yes, you are right. Thank you for your attention. So the option B is the correct option here. So we have the six different carbons. So that's why option B is here. It given six peaks. That one is the correct option here. Right. And in this molecule, I have just missed. So in this molecule, it will show the five peaks. Right. Right. Thank you so much. So now the question is, if we have not decoupled, so here it is mentioned decoupled spectra, right? Now we have to, for the same molecule, I will just rub this molecule. For the same molecule, we have to assign how will be the splitting look like, or how many peaks we will get in the NMR spectra. So for the same molecule, as given in this question. So if you look at this question, here there is one CH3 group there, right? That is, this carbon has the 1, 2, and 3, right? So three hydrogens are attached here for this molecule. So I will just highlight in the different color. So one, two, three. So what happened? Because of three uh, protons, this carbon will show initially triplet, right? So we get the triplet due to these three hydrogens. Not triplet, we get the quadrate. 2Ni plus 1. By that formula, we get the quadrate, right? We will get the quadrate due to these three. But if you look at the this one, this coupling is J1 coupling, right? Because it directly attached to this one. So it is also possible that this carbon can show the J3 coupling as well, or the J2 coupling. But if you compare this J2 coupling with this carbon, the natural abundance is only 1%, right? So that's why we not generally observe due to the splitting due to the adjacent carbon atom. But there are the protons available which are present about 99.98%, right? So because of this proton, uh, yeah, because of this blue circle proton, again this carbon, what will show? It will show triplet, right? So again each signal will split into the triplet. So the also you have to keep in mind, so I have written this quadrate. Is this quadrate is correct or incorrect? This quadrate is incorrect because according to the Pascal's triangle, the intensity I have written here is incorrect. The intensity of this quadrate should be 1s2, 3s2, 3s2, 1, right? So I have did the mistake here while drawing this intensity, but you should keep in mind this quadrate should have the intensity in this order: 1s2, 3s2, 3s2, 1. So these middle two lines should be longer in this one. So these two lines should be longer, but the curve. But anyway, what will be the splitting pattern here? The quadrate of triplet. So for this carbon one, uh, we will get the quadrate of triplet. Similarly, you can do for another remaining carbon. So I will just take in the new slide. Right. So for this carbon we have taken, right? Now if you want to do for the another this adjacent CH2, then now let's focus on this highlighted CH2 group, right? So it has the one CH2, right? And if you look at the another side, uh, I think here I'll just instead of this example, I think I have taken CH2 here. So let's take this molecule, this kind of any molecule, any random molecule, right? So here or here, let's say O, and anything attached. Uh, yeah, any R group attached here. So this is for the first CH3. Now take for this CH2. Can you drop? Can you tell what will be the splitting pattern for this CH2 group. So because of this adjacent two hydrogens, these two hydrogens, it will show first triplet, right? And again, triplet with the intensity 1:2 1. Then because of this adjacent 1, 2, 3, 3 protons, adjacent CH3 group, right? Adjacent CH group, it will show the quadrate. So each line will be split into the quadrate. Similarly, all this line will be in the quadrate. So here for this one, we will get the triplet of quadrate. So like this way, you can uh, solve the any splitting pattern for the undecoupled or uh, undecoupled 13C spectra. We have the same question based on the similar parameter. Here, this is the question. It is in the assignment. So here given CH3, I'll just draw CH3. Then we have the CH2, A, B, then the C double bond O. Again here, if you look at here it is written O. Then there will be a CH2 and CH3. So in this one, there are 1, 2, 3, 4, and 5. 5 different type of carbons. So 5 transitions are possible. So 5 transition, right? Then if you look at the in the question it mentioned in the coupled spectra. Here it is mentioned coupled, not decoupled, right? J 2J CH also observe, that is J3 coupling we can also say that also observe here, or J2 coupling also observe here. Then the multiplicity of the carbon A, B, C, D respectively will be. So let's take this is the A, right? This is D and this is E. So for as I have mentioned earlier, uh, let's take the for this CH3. So this CH3 it has the three adjacent hydrogen atom, right? So it will show the triplet in this manner, right? So it will get the triplet because of these three hydrogens. Then because of this CH2, what we will get? Sorry, it will get the quadrate because there are three hydrogens. So according to 2Ni plus 1 formula, we get the quadrate, right? With the intensity 1:2, 3:2, 3:2, 1. Then again this quadrate, each line of this quadrate will split into the triplet, right? So I will just take this line A. This will split again into the triplet because of addition. There are two protons available. So similarly, you can show the splitting for this as well as this. So what was that? The splitting pattern for this CH3 group, CH3A, it is quadrate of triplet, right? So this is quadrate of triplet. Similarly, if you look at this addition CH2, it will show triplet because of this two hydrogens, then quadrate because of these three CH3. This show this is the carbon atom which has here adjacent two CH2 attached, right? So it will show the triplet. Then if you look at this one, it has the two hydrogens attached, so triplet, and there are four hydrogens attached, quadrate. Then here, if you look at the methyl group, which has the quadrate of triplet, then because these three hydrogens shows quadrate and adjacent two hydrogens, so it will be a triplet. So you can match the correct option. So quadrate of triplet, quadrate of triplet is correct. Then triplet of quadrate, then triplet of quadrate correct. Then the triplet, this triplet is correct. Then triplet of quadrate, this is also correct. Then quadrate of triplet. So option A here is the correct option. So does anyone have any doubt in this question? So you should be able to solve this question, right? Because they are like quite simple. You just need to keep in mind the formula, that 2Ni plus 1, that formula. The next question is here. The 13C spectra is generally recording using. So here, as we have mentioned earlier, uh, if you have the any molecule, CH3, OH, right? So we are taking the, let's say, in case of 1H NMR spectra, since the natural abundance of these carbons are very less, so we will not observe any splitting due to this kind of carbon atoms. We will not observe any we will not observe any splitting due to this carbon. We only observe the splitting due to the addition CH2 or anything. So we generally record the 1H spectra as it is, right? But in case of 13C spectra, since this this nuclei, the carbon nuclei natural abundance is about 1%. But if you look at this protons, the natural abundance is greater than 90%, right? So because of this, NMR spectra show the splitting as we have solved the question. So if you look at this question, if you have the some simple molecule, then we'll, because of these protons in the coupled carbon spectra, we'll observe this many number of signals. And we know the, if you look at the organic molecules, we have the, in the generally any kind of organic molecule, let's take the example of this molecule. So let's say we have such molecules, and in these molecules, these all the nuclei, this all the carbon will show up in the aromatic region about 100 to 150 or 160 sorry, ppm, right? And if you look at the number of signals, there will be a here these four, and again this four multiplied by three. So one carbon itself show the 12 signal. So here also one carbon itself 12 signal. Here three. Here also again 12 and 12. So these many number of signals will be difficult to identify. So that's why we record the carbon NMR spectra in the broadband decoupling states, right? So that's why it's generally recorded in broadband decoupling state, just to stop the interference of the NMR active nuclei, like the hydrogens. Got the point? But if you look at the one example, let's say we have the CfH2, any kind of CH3, right? Let's take this example. So here there is one fluorine. Now when you are taking the decoupled spectra, the proton decoupled spectra, at that time what will happen? This carbon will not show the splitting due to this CH2, or will not show the any splitting due to this CH3 as well. So it will show 1, 2, 3 signals. But if you look at this carbon which attached to the fluorine, so the fluorine spin quantum number, how much, as we have already seen here. So this is the fluorine, and which has a half spin, right? So right. So because of one fluorine, it will show the doublet. So this carbon signal will be split into the two line because of the fluorine, and we will get the doublet due to this carbon. But the singlet for this carbon, also singlet for this carbon. Any doubt here? Why we are do the broadband decoupling in the 13C spectra, but not in the 1H NMR? Because of this reason, the NMR active like nuclei like proton, they show interference. That is, they show the splitting in the 13C spectra if you don't decouple the while recording the 13C. Here, one question is mentioned here. In the question itself given, the one proton decoupled carbon spectrum, two peaks are observed. So 1 and 2 peaks are observed. Just so we don't know where they are observed, right? So two peaks are observed here. So one peak is here, one peak is here, right? And the intensity is 1:2. So one has the higher intensity compared to other, about 2 times. And it is question itself mentioned the decoupled carbon spectrum, right? The proton coupled spectra for the same molecule. This is proton decoupled, right? So, and now let's say it is coupled spectra, proton coupled spectra, which shows the a singlet and a quadrate. So it shows the singlet and one quadrate. Quadrate has the intensity obviously 1s2, 3s1, right? And here one singlet. So like this, the molecule could be probably. All right. So we have given 4 different molecules, 1, 2, 3, and 4. So I will just draw the structure of each molecule. So this is the CH3, C triple bond, N. So this is the acetonitrile, right? This is not the option, but this is acetonitrile. Another is dimethyl acetylene. So here 1, 2, 3, CH3 and CH3. So this is the first, this is second dimethyl acetylene. Third is given 1,2-dibromoethane, right? CH2, CH2, Br, Br, right? 1,2-dibromoethane. And fourth given 1-bromo, 2-chloroethane. So, all right, now I will write here itself. Cl and Br, right? So these are the fourth option given here. If you look at the all the option, you should able to go to the correct option right now, because we have already seen uh, how the splitting look like for the in the coupled state or decoupled state. So let's do the first how the splitting looks like instead of going directly to the this one. So if you take this molecule in the coupled, in the sorry in the decoupled, how it will show? It will show only, since we are recording decoupled spectra, it will show two signal, two or one. Since the molecule is symmetrical, this will show only one signal in the decoupled spectra, right? And in the coupled spectra, D stand for decoupled and C stand for coupled. Let's say here, uh, decoupled and so coupled, right? In the coupled spectra, how it will show? So these both are identical, right? Because it has the plane of symmetry. So these both molecule, both CH2 are identical. So it will show only the singlet in the carbon decoupled spectra, and in the coupled spectra, because of this 2 CH2, it will show the triplet, right? So what it mentioned, does it matches? It is mentioned in the decoupled, it will show two spectra with 1s2, 2 intensity, right? And in the coupled spectra, singlet as well as quadrate. But obviously this is not option here, because in the decoupled it will show only one signal. So this is obviously wrong option. The another molecule is CH2 Br, again CH2 Cl. So these both carbons are different, not at all identical. So this will show the two signals in the decoupled, right? And in the coupled spectra, how it will show? It show, because of this CH2, it will show two triplet. And the intensity of this two triplet, if you compare the intensity, these both signals will be 1s to 1. So here also, this obviously only one signal, so we do not have to no need to compare. Here also one signal only. Here there are two signal with the intensity 1s to 1. Here also in the coupled spectra, it will show the triplet with the intensity of the this entire peak, which will be 1s to 1. But if you look at this, the first example, acetonitrile, in the acetonitrile, there is one CH3 and one carbon. So it will show in the proton decoupled spectra. In the decoupled, it will show one singlet, another also singlet, right? So it will show two signal here in the decoupled, and in the coupled spectra, it will show a triplet, right? Sorry, a quartet, because there are three carbons are hydrogens are attached, so it will show the quartet, and this carbon show the, because there are two adjacent CH3 are present, right? So three hydrogen present, so it will show, it will also show the quartet, because this will be the J1 coupling and this is the J2CH coupling, right? So that's why it, although it looks the same while writing the quartet and quartet, but the splitting pattern will be different for both the signals, because a J1 coupling constant is generally high than the J2 coupling. So this is also not the option. And if you look at the the last molecule, this dimethyl acetylene. So this CH3 will shows the quartet due to the hydrogens in the coupled spectra, and this carbon will show the, obviously, the quartet due to the uh, as it coupled with the adjacent CH3, right? So this is also and if you look at the intensity of this one, so the intensity should be uh, for this carbon, there will be, it will be intensity, the signal will be due to the two carbons, uh, this terminal CH3, and this signal also due to the two carbons. So this is kind of splitting will observe for this one. So which option correct here? In the question it mentioned, in the decoupled, the intensity is 1:2. All right. Then in the proton coupled spectra, we get one singlet and one quartet. All right. So anyone have any answer here? I will just check the answer. So answer given in the in this one is acetylnitrile, because it looks like they haven't do the mention due to splitting due to the J2CH, right? As we seen earlier in the earlier example of this, I think, as we seen in this example, although in the proton B, we can observe the splitting due to the adjacent CH3 also, right? But in the same one, in this one, since this carbon can also couple with this terminal CH3, right? So because of these protons, it will show 2JCH coupling, right? So in this question, if we ignore that 2JCH coupling, that time the acetylnitrile will be the correct option. Otherwise, acetylnitrile will not be the correct option here. Because if you look at this one, this will both are identical. So this option is the 1,2-dibromo is incorrect one. The again 1 bromo, 2 chloro. In that one also, if you look at the intensity of these two protons, will be the 1:1 in the decoupled spectra. So this is also incorrect option. Then we move toward the example of this dimethyl acetylene. In this case, in the decoupled spectra, we observe the two signal with the intensity. Intensity slightly varies from the singlet, triplet, or the quadruplet protons. So if you look at this one, so see there are three protons attached here. This is the tertiary carbon atom, right? Or the this carbon atom attached to only one carbon atom. So this is primary carbon atom. And if you look at this carbon atom, this is the quaternary carbon atom. In the 13C spectra, the quaternary carbon atom shows the intensity less. If we just draw the 13C, let me just should insert one new slide. So let's take this same example, CH3, triple one, C. If you took this example, if you look at the intensity of this signal A and B, although we get the signal due to the equal number of carbons, but this CH3 has the intensity higher intensity compared to the this quaternary, and this is the primary. Although this signal also due to the two carbon, and this signal also due to the two carbon atoms, but the intensity will be in this manner. So here the intensity should be for this one 1:3. That is 3 for this carbon and 1 for this uh, that quaternary carbon. And if you look at the another example of the acetonitrile, CH3C triple one N, right? So this carbon, we get the two in the decoupled spectra, we get the one signal and the two signal, right? The intensity for this one. So I will just give, if we look at this one, this carbon for this carbon A and this carbon B. So the intensity will be 1:3. And again, in the coupled one, so this will show if we are considering the 2J-CH coupling at that time, and generally it is observed because J2CH, as like we see in the proton, this will also the very will observe in the carbon NMR spectra. The splitting for this one will show in the manner of like this will show the quadrate, and also quadrate due to this 3CH3, and the B also will show the quadrate due to the same CH3 group. So in this one, if we ignore 2JCH, at that time acetonitrile is the correct option in this one, the question given. So as of now, you can select the acetonitrile as a correct option, but the condition is we are ignoring the 2JCH coupling, right? Because earlier in also in one example we have seen that 2JCH coupling is observed for this kind of molecules, and if you ignore that one, then the acetonitrile is the correct option here. Other options are obviously the incorrect one. Any doubt here in this question? Uh, if you don't have a doubt, can we move to next question? So we have solved this question also, right? This question also we have solved. All right. We have the next question here regarding the peaks observed in DPT 19 spectrum of the compound. It indicates that. What does it indicate? I don't think it is difficult question. I will just give another question also here. DPT 45 and 10th question, the same question for DPT 135. So just Google it. So you will get the correct option here. I don't think there is any rocket science in the finding the correct answer for this one, right? Also search for DPT 45 and DPT 135. You know, right? There are three types of DPT experiment generally we take: DPT 90, DPT 45, and DPT 13. So to distinguish between CH3, CH2, or quaternary carbon, we generally perform this type of experiment. The next question here is, in the 1H decoupled 13C spectra of CdCl3, three lines of equal intensity observed at 77 ppm. I think this question we have already solved in the last one, right? Why the CdCl3 show three lines in the at around 77 ppm. So you observe the sharp three lines in the carbon NMR spectra. Why this is? Although we are decoupling the proton here, but we don't decouple the deuterium 2, right? So this is the reason. I think, and also the I value for this deuterium is 1, not 1 by 2. So that's why, although there is one deuterium present, but if you look at the formula 2Ni plus 1, this formula, if you put the value of deuterium is I value 2 multiplied by deuterium is only 1 here, and also I value for this deuterium is 1 and plus 1. So it will comes 2 plus 1, that's the 3 option. So that's why we observe the 3 line in the deuterium NMR spectra. Sorry, in the 13C NMR spectra due to the deuterium. So which option correct here? Impurity generally seen in this is wrong. Coupling of CH proton with CH3 carbon wrong. Coupling of carbon with deuterium. This is the correct option here. So option B is correct option here. Also, when you are move to next, you are trying when you see the actual NMR spectra, I will give the some assignment to you. So in 1H NMR spectra, so where these peaks come from? Peaks at 1.5. Second, also there you observe peaks at 2.2. Third, we observe the peak at 7.26 when we are taking in CdCl3. And also fourth, at 0.0 ppm. Does any know any answer here? So where this peak come from?
7.26.
All right, 7.26. From what it come?
Singlet in 1H NMR and triplet in 13C.
Yeah, but at the in the 1H NMR spectra, when you take the 1H NMR spectra in CdCl3 solvent of any compound, you put any compound, we observe generally, these are the some peaks generally we observe. So from where this peak came? So this 7.26 is came from impurity of CHCl3 present in the CdCl3. So that's why the peak at 7.26 is observed, not due to deuterium, right? Also, if you observe, we generally observe the peak at 0.0 ppm, that due to the TMS that generally present in the CdCl3 water itself. It is served as an internal standard. Generally, most of vendors sell the CdCl3, which has the TMS already added. Also, we observe the peak at 1.5 or 1.56 around or 1.6. And this is due to the moisture. Also, as we know, we generally took the NMR spectra in the NMR tube, right? So we wash the NMR tubes with the acetone. So generally, this is also one of the sharp singlet. So even very small contamination of acetone present that also show at the 2.2 due to acetone. So these are the common impurities present in the CDCl3. And also, if you look at the DMSO, same parameter for DMSO, where the DMSO, that is CD3, S double bond O, CD3, right? So as we've seen already, in the CDCl3, there is possibility of presence of instead of this deuterium is if it not get replaced by this CHCl3 is also present because not 100% we can able to displace this CDCl3, right? Not 100% you can deuterate. There are still remain some hydrogens present. So that hydrogen shows at 7.26. But if you look at the DMSO, there are 1, 2, 3, right? And there are 6 total deuterium. So there how many possibilities are present that this deuterium is not getting replaced? So there are possibility like this one, right? CH, D, 2, double one, S double one, C, right? One hydrogen if it is not getting replaced, or there are also some possibility, right? That two hydrogens is not getting replaced. Similarly, if there are three hydrogens are not getting replaced, at that time we observe generally a broad multiplate uh, in the day of the DMSO uh, in the when you use the DMSO as a solvent. So I think you should keep this remember. Where are the impurity peaks? Impurity presented in solvent where this peak are. Otherwise, when you are trying to get the NMR data while concluding the or taking solving the NMR data, you may observe you may get in trouble if you don't know the value where this peak came from, right? Here is another question. The silicon 19 has natural abundance 4.7%. If coupled to 13C with abundance of 1.1%, then the SI spectrum, first option given, 13C will not couple. Second given, 13C couple will appear as satellite peak, right? Third option given, 29 SI will couple to the 13C, but coupling is not seen. This is obviously wrong. Where if it is coupled, then obviously we will observe the splitting or the coupling. Also, the SI 29 behave like abundance spin when coupled with the 13. So in this one, if you observe if you see the natural abundance of this carbon 13 spectra, it is almost 1.1, right? So very, very low. So in that case, what I observe, we observe one peak due to the very sharp peak due to the, let's say we have one example, Si and any other carbons are attached here. So carbon R3, let's take here. R is equal to hydrogen or any alkyl group or aryl group. So when you are taking this silicon NMR, we observe any a signal due to this silicon, and also there are directly attached carbons. So because of this carbon, we observe some. We will observe the release splitting, and they are appear as a satellite peak. That is the intensity will be very, very less. Generally, as we've seen, if you see the doublet, we'll have the 1:1 intensity. In the triplet, 1:2, 2:2, 1, that kind of intensity. In the quartet, 1:2, 3:2, 3:2, 1, that sort of intensity. But in this one, the intensity in the order of like 98 S2, sorry, 1:98 S to 1, that kind of intensity. That is these are very small peak you observe. We call it as a satellite peak. So in this one, the option B is correct option. The 30C coupling will appear as a satellites in the silicon 29 NMR spectra. So these are some problems from the assignment. Hope you are able to solve remaining. I think there are not any problem remain. So you should submit the assignment on time. I think it is stopped. Does anyone have any doubt here? All right, if you don't have doubt, we'll stop for today. Thank you so much for joining.